you doing? I wonder if Jordan is going to be joining us. So on the 19th, you want to go to the high school with us? Make sure to go to Kathy so you can fill out the paperwork. He said yes to you. He's done thinking. He said yes to you, Brian. So, and I'll give you a shirt. That's your reward. Actually, I'm mistaken. Parkway is on the Friday, the 22nd. If you want to come also with us to Parkway. It's not Thursday. Are you better for Friday? Do you have anything Fridays?
I don't have class on Friday.
So that'd be actually better for you. If you want to do it with us. Okay. Actually. Okay, let's see. Of course, what would I have it on? Okay. Let me go ahead and write this down. This is PHYS. What is it? 365 for 12/22. We're gonna be talking about quantum mechanics for the day. Okay. So the last class we talked and we derived the equation minus h bar square over 2m psi 2 squared derivative times 2 with respect to x squared plus e of x psi of x equals e psi of x. And we said the solution, this solution gives us the shape of the wave at t equals 0. Okay? said the psi of x of t is going to equal psi of x e to the minus I omega t. Okay? So basically, let's say you got this and you get your graph going in, and let's see if you're breaking it down to section. That's what you're using calculus anyway. Okay. The probability, so let me just write this down, y of x of t is an psi of x e minus I omega t. The probability density of px dx is going to equal to the integration from your limits from a to b psi x squared d of x. Now, what is this b of x? This is rho of x. This is going to be your probability density, which is your probability of finding the particle in a given space. So basically, you got this graph over there, and your probability of finding a particle in a small region of d of x. So basically, I guess this would be your region over here, d of x. Right? In that little region over there, that we can probably find the particle, which is your probability density, p of d of x, is going to equal the integration from a to b, wherever a is to b is, okay? Psi squared d of x. Okay? Now, this equation is time dependent. That means you psi x of t square is going to equal u psi x absolute value square. We said psi x of t was what? E psi of x e to the minus I omega t, right? So this is going to be the absolute value of e minus I omega t squared, which, if you actually do both of them, this is going to equal to what? To 0. Sorry, not 0. To 1. Right? It's going to be e to 0, right? So this is going to equal to psi of x squared. That means your probability density solution is independent of time. So basically, the question is usually find the eigenvalues or eigenenergies and eigenfunctions of a quantum particle in an infinite square well. So we take that little section that we had, okay, earlier. So let's say you're going from 0 to A. The places that you do not have a particle is going to be, V of x is going to equal to infinity. Over here, your particle is in the box. Let me just put this down. Particle and box, where your V of x is going to equal to 0. Think of it as a potential, right? Let's say. So think of it as a potential. Actually, I don't like this. Let me just write it. Exponential. Potential. So if you have a bunch of charges, those charges go from the higher potential to lower potential. For instance, a ball will fall from a higher gravitational potential energy to a lower gravitational potential energy. Will fall from the higher gravitational potential energy to a lower gravitational potential energy. We say its potential is, when you get a ball over here and it goes down, what's happening with the potential is what is going to be decreasing, right? Because you're going to get high potential, you're going to go down, so the potential is decreasing. Same thing. Your V of x is going to equal infinity. That means the particle is not there. We know the particle is sitting in the square well. It's inside over here. That's where we use the Schrodinger equation to find where it's at. So let me just go ahead and write this down. So, same thing. We're saying V of x is going to equal infinity. That means it says the particle is not there. Now, we know the particle is sitting in the square well. Now that's what we use Schrodinger equation to find out the where. Actually, let me just write this down. Find out. Let me just go ahead and get a different color for this one. The where and how. The particle lives between the walls. Okay? So going back, let me just, okay, go ahead, back on this one. So basically this is 0 to A. Your v of x is going to equal infinity on both of these sides. That means that's where the particle is not there. So the question is, what are the allowed states for the particle to live there? And the other question is, that's one question. One question is, what does the probability density look like? The probability density function look like? In other words, what are the eigenenergies? Or in other words, allowed eigenenergies. So you get the particle lives between 0 to A, right? What are the allowed states for the particle to live there? What does the probability density function look like? And what are the allowed eigenenergies, right? So your answers to those questions determine which wave function psi satisfy the boundary condition. And let me actually just write this down. BC is boundary condition. So answers to questions determine which psi satisfy the boundary condition imposed by the parameters imposed by Schrodinger. See, the boundary conditions, actually before I forget, let me go ahead and save this, just in case, because you know about this time it likes to crash. Okay, so your boundary conditions tells us the particle not located at infinity. That means that the probability density function must equal to 0. Equal to 0. So the boundary condition of the particle is not there, located at infinity, right? That means the probability density function must equal to 0. If the particle is not there, the probability of finding it will be 0. Which makes sense, right? If the particle is not there, that means the probability of finding it there will be 0. Which means your probability density function is going to equal to 0. Alright. So let me go ahead, get my pen. So there's your x, right? 0 to a. Over here, there's no particle. That means your v of x is going to equal to infinity. That means your probability of finding a particle over there is 0. Your wave function is going to be 0. Same thing on this side, your wave function is going to be 0. The probability of finding a particle is going to equal to 0, where v of x is going to equal to infinity. Over here, your v of x is going to equal to 0, because there's a particle. Your psi of x is not going to equal to 0. Now, where your probability of x is going to equal psi x star invert psi of x. So your basic conditions is your psi of x is not going to equal to 0, where x is between 0 to a.
What is that? Probability density equal?
This?
Okay.
This one? Oh.
Yeah, that.
The star, conjugate. Conjugate becomes I minus I. You know what I'm talking about? Yeah. You still writing? Yeah. You good? So your time. Set this. Oh, like, oh, it's like big there. So your time independent Schrodinger equation is minus h bar squared, which is over 2m b2 psi over dx squared is going to equal e psi. Now, if we resolve it, what you're going to have d2 psi over dx squared is going to equal to, what is it, minus 2me over h bar psi of x. Let me just write down as a function of x, you see what I'm saying? You with me so far? Now, if you remember, we had a k that equal to what? Remember our k? What did it equal to? 2me over what? Over h bar, right? That means your k squared is going to equal to 2me over h bar yeah, that's better. 2me over h bar squared, which looks like this little fella right now over here, right? So we can substitute k in there. So d2 psi over dx squared plus k squared psi is going to equal to 0. Understand what the k? Kinetic energy, right? Now, we must solve this second order differential equation. And when we do, we find all psi values value psi can take to satisfy this equation. So we must solve this second order differential equation for psi to find out what it takes to satisfy this equation. Okay? It was like saying, it's like saying, for example, ax squared plus b of x plus c equal to 0. How can you solve this equation? We find all values of x that can satisfy this equation. And in this term, a, b, and c is going to be what? Your constants, right? So here's our equation, d2 psi over dx squared plus k squared psi equal to 0. Okay, we want to solve for psi, okay? Let me go ahead and write this equation back again over here so we can start on it. So, d2 psi over dx squared plus k squared psi equal to 0. If you want, you can do as a function of x. Let me just write this down. Okay. So let's go ahead and try psi of x equals x. So let's try a solution of psi of x equals to x. Okay, so psi of x equals to x, that means d2 psi over dx squared is going to equal what? To 1, right? X go back, second derivative equals, let me just dx over x is going to equal to 1, which means your d1 over d of x is going to equal to 0, right? From x to 1, 1 to 0. So what that means is, if that's the case, that means this little fella is going to go to what? To 0, right? The first term, right? Because it's 0, 1, yeah. So, which means, let me go ahead and write this down. Your k square x is going to equal to 0. Okay, so you have kx equals 0, right? When is this true? This is true when is that true? It's either k or x is going to equal to 0. Does that make sense? Right? But here's the problem. K is, remember what k was? Square root of 2me over h bar, right? So k is dependent on the energy. If k equal to 0, then that means the energy, if you solve for the energy, is going to equal to 0, right? Which means there is no particle. So, which is not good. If k equal to 0, that means the energy equal to 0. If the energy is equal to 0, that means there's no particle. What did I touch? Alright, so your k is dependent on the energy. If k is 0, then the energy is 0, that means you have no particle. Let me go ahead and write this down. If x is 0, that means psi of x equal to 0, which means that p of x is going to equal to 0, which also means that there's no particle. So that's not a useful solution. So psi of x equals x, that's what we had from the beginning, right? Psi equals of x is not a useful solution. because we know that there's a particle in there. Particle in there. Okay, so psi of x is not going to work. All right? Okay. So I'm going to give you, usually you want to do, because we have an equation, we get a wave, so we're going to define it as a sine and a cosine wave. Okay? So let me go right ahead. 2 psi of x dx squared plus k squared psi of x is going to equal to 0. Now let's propose a solution for psi of x is going to equal a sine k of x plus b cosine k of x, where a and b are constants we yet don't know yet. We don't know yet. And we're going to say that this is, let me get that right. We're going to say that this equation is a solution of the time independent Schrodinger equation between the walls of the well. Alright, so we're proposing for that psi of x equals a sine k of x plus b cosine k of x. A, b are the constants that we need to know what they are in order to solve this. Okay? Alright, perfect. We said that t2 psi of x equals k squared psi of x dx. Let me go ahead and write this down. I'll just wait for you. X equals a sine k of x plus b cosine k of x. That means d psi of x over d of x is going to equal to what? So your first term is a, then there, sine, it becomes cosine, k of x multiplied by k, right? And then you get b, cosine becomes minus sine, k of x cosine sine k of x, right? And your second derivative is going to be equal to sine becomes minus cosine, so minus k a sine k of x squared minus k squared sinus cosine b cosine k of x. Now let's plug this. Plug into psi square of x v of x plus k squared of psi of x equal to 0. I just call this equation 1. So we're going to plug this in, right? Here's your psi over here. Psi squared of x is over here, right? So, in doing so, what we have minus k squared a sine k of x minus k squared b cosine k of x plus k squared times a sine k of x plus b cosine k of x is going to equal to 0. If you actually open up the parentheses, what you're going to have minus k squared a sine k of x minus k squared b cosine k of x plus k squared a sine k of x plus k squared b cosine k of x is going to equal to 0. And if you notice, what do we have? We have, k squared a sine k of x minus k squared a sine k squared of x, right? Minus b. So guess what? 0 equal to 0. Everything cancels out to be 0, so that satisfies the solution equation. So let me go ahead and hit that down. Everything cancels out to be 0. So this satisfies the Schrodinger equation. So let me go ahead and go over here. Go ahead and say before it disappears. So here's our well over here. To a psi of x is going to equal to 0 over here, where v of x is going to equal infinity. V of x is going to equal to infinity, where that means your wave function is going to equal to 0. We said the probability is 0. Over here, your psi of x is going to equal to a sine k of x plus b cosine k of x. Where v of x is going to equal to 0. So psi of x, let me just write this down, is sine k of x plus b cosine k of x, where you bound this condition, your psi of 0 is going to equal to 0, and the psi of a is going to equal to 0. Psi must equal to 0 at the boundaries. So if you actually break it down, right? Let's break it down to the sine and the cosine, right? So so let's say I got this, and I'm gonna write this. Let's say this is your sine wave. So you go from here to here to here. So you go from here to here. Amplitude 1 minus 1. And you say this is your cosine. This is your 1. This is your minus 1. So this is your fx equals sine of x. This is your fx equals cosine cos of x. And we said x is 0, so you'd be sine of k of 0 is going to equal to what? To 0, right? Which means sine cosine of 0 equal to 0. Cosine k of x, sorry, k of 0. When x equals 0, your cosine k of 0 is going to equal to what? 1, right? Makes sense? Because cosine of 0 is going to equal to 1. You good?
Oh, that's your, what is it, sine k is 1?
Yeah, remember we have, it's a sine k of x plus b cosine k of x, right?
Mm-hmm.
So if you look at each one of them, right? Mm-hmm. Here's your sine, here's your cosine. Sine k of x, sine cosine of x. And when x is 0, let me just write this down. X is 0, right? Mm-hmm. That means sine k of x. That means sine k is 0 equal to 0, right? Okay. Does that make sense now?
I thought, okay, that's what, how you write 0. I just thought that means like empty or something.
Oh no, 0. Yeah. That means cosine k of x, which is cosine k0, cosine k of x, which is cosine k0, which is equals to 1. Make sense? This means that psi of 0 is going to equal a sine k of 0 plus b cosine k of 0, right? You with me so far? Mm-hmm. Which we said this is going to be equal to what? Is going to equal to 0, right? And this is going to equal to what? To 1. Well, if that's true, so in order for psi 0 to equal to 0, right? That means if cosine 0 equals to 1, that means this little fellow over here, right? Be equal to 0, right? Does that make sense? Because a is going to go to 0 anyway, because sine 0 is 0 anyway, right? So we can have a solution of this is going to go to 0 anyway, right? P cosine k of 0 is going to go anyway. So the solution of psi of x is going to equal to a sine k of x. With boundary condition 0, 0 is going to equal to 0, and psi of a is going to equal to 0. Your boundary condition from 0 to a, right? Well, if we set a is going to equal to 0, what's going to happen? That means psi of x is going to equal to 0 for all values of x. That means your probability density is going to equal to 0 for all values of x. That means no particle. So this is no brainer, wrong. So basically, your A equal to 0 will not work out. You good?
I'm just wondering, okay, so psi of 0 equals A sine K0 B cosine K0. If sine part goes to 0 when you, whatever that thing is,
What?
your function, you don't look at the cosine part, you just...
The cosine is going to 0 anyway because k is 0, 0. I'll explain in just a second. Because it's going in full revolution. K is 0 is going to go 1. So your B is going to go to 0 anyway.
Right.
So we need to find out what's A. What's your A function?
Okay.
You see what I'm saying? You got it? Yeah, because, and that's a good question, because here's the deal, right? So,
I didn't finish right.
oh, I'm sorry. Hold on, I was going to explain.
It's no particle.
Actually, let me just write this over here. Just a second. Let me just adjust this so it can actually be understandable. Let me just say k of x is going to 1 and 0. You see what I'm saying? Cosine k of x is going to 1. That means b is 0. Is that better? Is that better?
Yeah.
So, when you actually look at the sine wave, right? So this would be your pi. This would be your 2 pi, 3 pi, etc., right? So sine k a is going to equal to 0. This is when what? You have, when sine is going to be equal to 0, when it's pi, 2 pi, 3 pi, 4 pi, right? So when it's n pi, right? So Ka is going to equal to n pi, or you can say k equals n pi over a, where n is an integer, right? And this is your fx equals sine of x. So n is an integer, right? So fx, let me go ahead and write this down. So f of x is going to equal to k of x, not k, sorry, sine k of x. And a is 1. Okay, and that means f of x is going to equal sine n pi x. Because again, remember the k? It was n pi over a. A is 1, so it'll be n pi x, right? You with me so far? So if you looked at this, right? What's n over here? It's 1, right? 1 pi. You see what I'm saying? And this is your n number. It's the one with the pi, right? What's n over here? 2. What's n over here? 3, right? So let me go ahead and draw this down. So this goes from 0 to 1, n equals 1. That means there's your wave function for n, wave function 1, right? And you get your eigen energy 1, okay? And let me actually go do this. Anyway. The second one goes again from 0 to 1. This is E2 for psi 2, where your n equals to 2. And this goes boom, 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 boom. Think of it as the humps. 1, 2, 3. That's the number of n's, right? Make sense? So n equals 3 for this one, which means you got eigenvalue 3, where psi 3. So each n value gives us a solution to Schrodinger equation. Your k is dependent on the energy also. K is dependent on what? On n, right? So if K depends on, if K depends on the energy and K depends on n, that means the energy also depends on n, and that's what we see in E1, E2, E3. So basically, each n gives us a different eigenvalue, eigenfunction, and eigenenergy. Okay? Each n gives us a eigenfunction psi of n and eigenenergy. E of n. N must be an integer to satisfy the boundary condition to achieve quantization. But here's the thing, right? We talked about A, but we have not yet solved for A. We still need to solve for A. Now, to normalize that wave function, we go do it as such, psi over psi, and let me actually write this down. Represent normalization or normalization of psi. So your normalization of psi is going to equal to your integration from 0 to a psi conjugate psi d of x equals to 1. And this is what you do. So this one, the quotation represents the normalization of psi, this to normalize it. To normalization, where again psi of x, let me go ahead and write this down, a sine k of x where k is going to equal n pi over a. Now here's the thing, right? So we don't have a complex function, right? We don't have an I. We don't have an imaginary. We don't have either I, right? So psi conjugate. So should I write over here or the next one? Let me just see. Did it? Yeah, let's write it over here. Actually, let me write it on the next one. So psi conjugate psi is going to be the same what? Is the same as what? As psi squared. Does that make sense, right? You just multiply the same function, right? So psi is going to equal to what? We said is going to be a sine k of x, right? That means multiplying them together, what you're going to have? A squared integration from 0 to a sine squared k of x d of x equals to 1. Now, if you remember, we have a mathematical rule that says sine squared theta is going to equal to, actually, let me make this a little bigger. I have room to write this. Sine squared theta is going to equal to 1 minus cosine 2 theta over 2. That means which is going to equal to 1/2 minus cosine 2 theta over 2. Well, what a coincidence. We have a cosine, a sine squared right over here. Right? So we can substitute it. So psi, the conjugate psi is going to equal to a squared times the integration from 0 to a to 1/2 minus cosine 2, the angle is kx, so kx divided by 2 let me just go ahead and close this whole thing. D of x is going to equal to 1. So psi over psi is going to equal to a squared integration from 0 to a 1/2 d of x minus from 0 to a cosine 2k of x over 2 d of x is going to equal to 1. Okay? So taking this one from 0 to a, 1/2 d of x is going to equal to what? X over 2, right? From first initial to last initial from 0 to a, which is going to equal to a over 2 minus 0 over 2. This is going to go to 0. So this is going to equal to a over 2. That means from 0 to a, cosine 2kx over 2 d of x is going to equal to the second term, right? We're doing the second term. Your sine 2kx over 2 times 2k is 4k, right? And let me actually go ahead and write this down. 2 times 2 of k from 0 to a, and it's going to equal to sine 2ka over 4k, right? Minus, this is going to be 2 sine, I will say just sine 0 over 4k, which this is going to go to 0 anyway, right? You with me? So it's going to equal to sine 2ka over 4k. This means that psi is going to equal to a squared, a over 2 minus sine 2ka over 4k is going to equal to 1. Which means that a squared, a over 2 minus sine 2n pi over 4k is going to equal to 1. But then 2 times an integer is going to still give me an integer, right? n pi, 2 pi, 4 pi, things like whatever is going to go to 0. So this little fella is going to go to 0. So this means that a squared multiplied by a over 2 is going to equal to 1. That means our solution for a is going to equal to square root of 2 over a. Which means that's our solution. That means we can substitute it back in that main equation. That means our psi of x was going to equal to a sine k of x. This little fella is going to be square root of 2 over a. Again, your k is going to equal to n pi over a. That means your psi n, your eigenfunction. Actually, let me go ahead and write this down before I continue. EIGN function is going to equal to your a, which is going to be square root of 2 over a sine. I'm just going to call this k of n. You see what I'm saying? Because n depends on n, right? N pi is it. So I'll just say k of n. No, let me just go back to my same color. K of n times x